To hold all your math awards, you need a cardboard box with a volume of 28,000 cubic centimeters and no lid. But cardboard is expensive and you're not made of money. So you decide to use as little cardboard as possible. What are the dimensions of the box that minimize the amount of cardboard used? How are we going to measure the amount of cardboard used? Area. Surface area. So let's draw your open top box. So an open top box, when I was in first grade, I remember my friend Jerry showing me how to draw an open top box. Jerry said, draw one rectangle like so, and then draw the other one a little bit like off, just a little bit translated, and then kind of behind it like that. Don't ask me why I remember that. I haven't seen Jerry in 40 years. I don't remember his last name. I'm not as old as Jerry Seinfeld. So I think it makes sense to call this dimension here x, the length of that horizontal dimension x. And then actually it makes more sense if we go with the usual order. I guess it doesn't matter, but it would make more sense to call the depth dimension x. Doesn't matter though. And then y usually goes back and forth, and then z, of course, for the vertical dimension. So what would, if the top of the box is open, what would the area, I'll call it A for area, of this thing be? Sure, so x times y would be the bottom face, and there is no top face, right? So that'd be the area of the bottom face. Plus the other ones, there's 2 of each. So there'd be 2, it doesn't really matter the order, 2yz plus 2xz. Does everybody buy that? And so you actually want to minimize, our goal is to minimize this function, isn't it? Would you buy that? Because the minimum area is going to correspond to the minimum amount of money spent on cardboard, since you're so cheap about your math awards. Now there's an auxiliary equation here that we can use to get, okay, that function has 3 input variables in it, right? But the methods you were taught only involve 2 input variables, so we have the volume formula we can create to get it down to 2 inputs. So what would the volume of this thing be? Volume would be xyz, and we know that that is what? 28,000? I know. I'm having that kind of day too, so I understand. I'm going to solve that for z in terms of x and y, just because I like having things in terms of x and y. So I'm going to say, excuse me, I'm going to say that z is equal to 28,000 divided by x times y. Okay, so let's get our area as a function of x and y. I'll even call it a of x, y. So what would a of x, y equal? X times y plus...
56,000.
Yeah, it would be 50. You want to do that all at once? I don't blame you. So 2 times, okay, we're going to be plugging in for the z, right? We're going to be plugging in this value. So you're going to get 2 times the 28,000 in front. Let's make that 56,000 right away. Y's cancel, and so what are we left with? Just divided by x. And then for this one, repeat but with y. I like that. Does everybody believe that? So, okay, so that's our function. We want to minimize it. What do we do? Partial, partial, partials. So the derivative of a with respect to x, leaving off the function notation, what would that be? Okay, so y minus 56,000 over x squared. Does everybody believe that? You could, if you didn't believe that, you could rewrite this as 56,000 times x to the negative 1 and just use the power rule on it. That's what you'll get. You'll get negative 56,000 over x squared. And then what's the derivative with respect to y? Okay, so yeah, there's a nice symmetry going on here. Derivative of this guy with respect to y would be x. Derivative of, okay, this guy goes to 0 this time, right? And then the derivative of this guy with respect to y, we get the minus 56,000 over y squared. Okay. And then what do we do with both of these? Set them equal to 0. Now, okay, you do have to be careful when you multiply through by a variable in some cases. But do we have to worry about that here? No. Are we interested in when x or y is equal to 0? No. In fact, if you look at our area function, x and y can't equal 0, right? You'd have it wouldn't be a box. It'd be flat. Yeah. So we can assume it's safe to assume that both x and y are non-zero, and that's when it's safe to multiply through by the variables, right? To clear the variables in the denominators. So it's not an issue here, but I wanted to mention it because sometimes it is an issue, as you've seen in the homework, right? So what I'm going to do is I'm going to clear the fractions here. And if you didn't like that, you could find common denominators and add and then look at the numerators because that's what determines when you get 0. So if you multiply through by x squared here, what do you get? So you multiply by x squared, both sides of the equation. What do you get? X squared y minus 56,000 equals 0. But how about just, I like what you said, equals 56,000? Does everybody believe that? Does everybody see where that comes from? Clear the fractions and then add 56,000. Clear the single denominator, that is. And then here, if you multiply through by y, so times y squared, what do you get? Xy squared equals 56,000. Okay, does everybody believe that? Some of you look a little incredulous. Yeah, you okay? All right. So what can you say about the left-hand side of both of those equations? If they're both equal to 56,000, what about the left-hand sides? They're equal. Okay, so we get, let me go over here, get as much room as I can. So we get x squared y equals xy squared. Now, if we wanted to, we could divide up the variables here, but it might be just as easy to think of in terms of factoring. So if I set this equal to 0 by subtracting xy squared from both sides, what could I factor out? X and y, and I'm really not interested in that factor x times y, right? But I am interested in what's inside here. What do I get? X minus y. So I get x times y factored out, and then x minus y inside the parentheses. That's a multiplication right there, and then equals 0. Oh, and then that gives me, I'm not interested in when this is equal to 0, right? We know x and y aren't 0 here. So that gives me y equals x. That's not as bad as it looked, right? Now, where can okay, that's great, y equals x, but I need to get some numerical values here. So does anybody see an equation? Actually, there's a couple of them you could plug back into. So let me clean that up a little bit. So y equals x, and then, well, I suppose I could plug in, right? Let's see, if I want to plug in x for y, I suppose I could plug it in right here. What would that give me? X cubed equals 56,000. Does everybody buy that? Okay. So x would equal the cubed root of 56,000. And what does that turn out to be? I think we can do better than that here. We're better than that. Let's not get decimals. 20 cubed root of 7. How do you get that?
You make like this old-fashioned shrewd break it down.
Okay. an old-fashioned tree and break it down.
Yeah.
That's correct, actually. 20 cubed root 7. I will let you guys verify that. And then, well, y has to be the same thing, right? 20 cubed root 7. And, okay, how could you get z? Which equation? That one. And I think if you simplify that, don't you get 10 cubed root 7? I'm going to let you guys verify those three. It takes a little bit of algebraic manipulation, but you guys can do that. Oh, one thing I should do, though, is put in units. What are the units? Centimeters? So, well, what are the linear units? So let's go centimeters, centimeters, centimeters. One thing I might mention is we haven't done the second derivative test. All we've found is a critical point. But you could argue by the nature of the problem, though, that there has to be a minimum surface area. There doesn't have to be a maximum surface. Play with the dimensions, convince yourself. If you want, you could use the second derivative test here on the x and y values that we got, right? But I would argue just by the nature of the problem, there has to be a minimum and not a maximum.